Hello, my name is Lucas Leandro Nesi. I am a PhD student in URGS Brazil, advised by Professors Lucas Melo Chinor and Arnaud Legrand. I am going to present our work, exploiting system-level heterogeneity to improve the performance of a GeoStatistics multi-phase task-based application. Over the last 2 decades, heterogeneity in HPC has become a necessity, not only at intranode with accelerators, but at a system level when machines are different from each other. This is very perceptive when we analyze supercomputers like Brazilian Santos Dumont or the French Janzai, that each one have 4 main partitions. Heterogeneity is also found by scientists willing to easily access cheap resources, for example in the cloud, where there are dozens of instance types that can be freely combined. So the problem that I will discuss today is how to distribute an HPC application on these heterogeneous resources. So the application that I will consider is GeoStat. It was designed by Cost, and its goal is to predict mixing observations in geostatistics data, like in climate applications. It is a task-based application that uses Chameleon and StarPU, which allows both to easily and efficiently exploit CPUs and GPUs and to design a mixed precision code. GeoStat had this efficient show with 4,000 CPU only nodes, where they studied the performance again is using mixed precision. The data of GeoStat is a set of points in the space, and the value of their observation z. GeoStat fits a Gaussian model with the matter kernel, with a scale parameter theta. The quality of these fits depends on it. Hence, GeoStat optimizes theta to maximize the Gaussian likelihood function, where we have to compute the determinant and the inverse of the matrix sigma theta. Both can be easily computed on sigma theta has been factorized with a Cholesky decomposition. The main structure of the optimization iteration is guess a new theta, then do the matrix generation, the factorization of this matrix, the determinant, the solve, and the dot product. Since an application has been developing using the task paradigm, it has a DAG that's submitted to the StarPU. We can see here the dependencies between tasks. Consequently, there is no need for any operation synchronization. Also, we can see the complexity of these steps, where the factorization is n cube, while the generation is over n squared. First, to characterize the execution and understand it, we show one iteration of synchronization between phases. In the image, we show the Cholesky iteration progression in the top. In the middle, the Gantt chart presents the resource per node aggregate utilization, where each task is a color, and in the bottom, the total memory used in the function of time. Here, we can see 3 very distinct phases: A, the generation, B, the Cholesky, and C, the 3 minor phases. And to maximize resource utilization, to truly use heterogeneity in our favor, we need to make this asynchronous, and remove the synchronization between phases. We can see that the generation only happens on CPUs, and factorization could start as soon as data was generated. So, if we remove the synchronization points and let the task-based runtime take care of the phase overlapping. In the left, there is the synchronous vector, in the middle, the pure asynchronous one. That we can observe that has idle times in the resources. Unfortunately, it's not that easy to obtain optimal synchronous execution. Many technical aspects have to be handled, ranging from algorithm changes, priority adaptation, memory management, and resource oversubscription. So we propose and discuss many optimizations detailed in the paper, to get a very smooth execution and good phase overlap. Here, we can observe that the optimizations really improve the performance when compared to the original synchronous version, up to 50% in performance gains in some cases. Now, with these conditions, we can study how to distribute it across heterogeneous nodes. The problem is that phases have interaction and preferences for the resources, where tasks have different speeds per resource. So we cannot compute distributions per phase individually. So to correctly compute how much of each phase should execute per machine, consider phase interaction, we formulate a linear program. Here, we have T for tasks, R for resource, and S for steps, and the steps are imaginary divisions that we make in the matrix by the diagonal, present in this image. This represents more or less the flow of the algorithm. Then, we have variables that represent the ending time for the generation step, GS, and factorization step, FS. Basically, when one diagonal is done for each phase. We also know how many tasks we have per step, that is key ST. And because it's a task-based application, we have the duration of each task on each resource, the WTR. And the variable that we are trying to optimize here is alpha, the number of tasks of type T of type S to be placed on resource R. So the goal of the linear program is to minimize the execution. We can do that by saying that our objective is to minimize the sum of the end of the phases. And we have a conservation rule that says that the sum of all tasks that I place is equal to the number of tasks. And we also trying to control the execution flow here. So we want to say that one generation step can only happen after the previous one ended. And we know that the factorization for a step can only happen after the data was generated. And we should control the flow of the factorization steps. And we have to guarantee that two tasks don't execute at the same time. And we will also adjust the first iteration a little bit. With this linear program, we can compute the interaction between phases and compute the total power per resource. However, even after we know the powers, we cannot do the distributions individually per phase. So first, let's consider this scenario here where we have 4 machines, where 2 only have CPUs and 2 have GPUs. And the generation only uses CPUs, but factorization uses CPUs and GPUs. So nodes 3 and 4 should receive more load in factorization. If we create the distribution individually, we can have a factorization distribution using a heterogeneous algorithm, 1D1D, and we can have a block cyclic distribution for the generation. During the execution, the blocks that are different in nodes in each phase need to be communicated. So in this example, the total communication is 890. To reduce communications, we propose an algorithm that's in the paper that uses the factorization distribution as a baseline and compute a communication improved distribution for the generation. This case only has 517 communications, a reduction of 41%. To evaluate the strategies, we use different types of nodes. In this execution here, we have 4 nodes without GPUs, the SHTMs, and 4 nodes with the GTX 1080, the shiftless. We can see by the Gantt chart that the execution is very good with low idle time. We also can see that factorization starts as soon as possible in the GPUs, and the CPU only nodes the transition of the generation factorization is smooth. And we can compare our strategies with the standard executions today and the state-of-the-art distributions. We have 2 situations here, 4 plus 4 nodes and 6 plus 6 nodes. In red, we have the case of using a block cyclic with heterogeneous resources. That is very bad. In blue, we have the standard today, that's to only use the fastest machines with block cyclic. In green, we have the 1D heterogeneous distributions that were done individually. And in purple, we have our strategies. The linear program bounds observed by this white area here. In this 4 plus 4 situation, we can observe that when we add slow machines and use heterogeneous distributions, the blue to the green, we improve the performance. But in this case, heterogeneity was not high enough, and the original 1D individual distributions were already very good. However, to accelerate the factorization, we can start adding other types of nodes, very fast ones with the P100, for example, are the shiftless. And in this scenario, with 3 levels of heterogeneity, with 4 plus 4 plus 1 and 6 plus 6 plus 1 nodes, our strategies perform better. First, adding slow machines always helps. Create a system level heterogeneity, and in these cases here, when we compute the proportion of each phase to give to each node, consider phase interaction, and build distributions related to another, we improve the performance. We can also analyze the Gantt chart of the 4 plus 4 plus 1 case, and we can see some idle time and problems. This happens because of excessive communication and factorization, the network hardware limits, and runtime decisions. And even if your version is better than the others, include the original 1D, the distance to the linear program and these idle times here clearly show that we can do better. So to decrease communications, we can limit the factorization to only the fast 5 heterogeneous nodes. Still, the slow nodes with only CPUs are used to accelerate the first phase, the generation. This improves the performance. we should be able to have programs that can take this kind of decision, of which nodes to use and how to distribute the load. However, anticipating communications in this asynchronous and heterogeneous world is very hard. So we should be able to learn and adapt to this unforeseen situation. So this is what we are investigating as a consequence of this work. So remember the big question of this work? How to distribute an NPC application on these heterogeneous resources? Okay, the answer is that it is complex, because you cannot ignore any detail. You show that we need a synchronous phase execution with the correct overlapping strategies and optimizations to further improve performance. And because heterogeneity makes all these problems worse. And heterogeneous multi-phase distributions are not individual responsibility per phase, but you have to consider the interaction and communication across phases. However, we show that when we invest in solutions for all these problems, node heterogeneity can improve the performance, using all the available resources. In the end, with all the strategies, we are able to gain in the best case 68% compared to the synchronous execution. And the next challenge is to learn and adapt to these foreseen situations. So here are the acknowledgements of this work, and thank you for your attention, and I am open to questions.